Hi, my name is Akin Hyatt,
Hi, my name is Lauren McCaffrey.
and this is our OPTI 471B Lab 1 summary.
Our first objective was to align the laser beam to the table. We placed an adjustable iris at two planes in front of the laser and then observed the laser beam position on the iris in order to adjust the alignment of the laser. We either translated the laser beam using the translation stage or adjusted the rotation knobs on the laser beam mount in order to get the alignment. This resulted in a total of 4 degrees of freedom that we used in order to get the perfect alignment of the laser beam. Then check the table levelness by directing the aligned laser beam onto one of the faces of the pentaprism, which then folded the beam 90 degrees towards the tray filled with water and observed the reflected beam from the water. Given that the water was level with the ground, if the reflected beam was not collinear with the incident beam on the water, that was an indication that the beam was misaligned. This setup was also useful given that the beam was not impacted by the rotation of the pentaprism. We created orthogonal beams with one laser using the pentaprism and cube beam splitter. The alignment of both techniques was similar and required aligning the back reflected beam on the laser from the pentaprism using the tip tilt adjustment knobs and the reflected or 90-degree folded beam with the translation and rotation of the prism. Ultimately, we needed one less degree of freedom to align the pentaprism compared to the cube beam splitter, given that it automatically folds the beam by 90 degrees. Therefore, we learned that folding a laser beam is easier with a pentaprism and applied this technique in the following sections.
Using the techniques that we discussed earlier to create parallel and orthogonal beams, we're able to co-align two lasers using a beam splitter. The second laser is aligned using the same technique as the first, with the pinhole. We'll use a pentaprism then to fold the beam and create an orthogonal one, which will be combined with the red laser at the beam splitter, thus producing a yellow spot.
To align each of the lenses in the Keplerian telescope system, we first adjusted the 2 translation degrees of freedom and then the 2 rotation degrees of freedom, checking both the back reflection and transmitted beam movement during the process. We opted to align in this order given that the translation mounting components were more sensitive than the kinematic lens mount. Here you can see we used a variety of techniques to observe the movement of the back reflected and transmitted beams in order to overlap and center all beam paths to the laser beam axis. We first aligned the 75mm focal length eye lens and then the 200mm focal length objective lens in the Keplerian telescope because the shorter focal length was more sensitive to alignment error. We could verify our alignment by observing a collimated but enlarged beam exiting the system.
In order to align our microscope with our laser, we need to make sure that the crosshairs of the microscope line up with the optical axis, as well as the transmitted beam through the microscope being lined up with the crosshairs. When aligning the microscope, it's important to control 4 degrees of freedom, the translation in the X and Y directions, as well as the tip and tilt of the microscope itself. We know everything's aligned when the beam lines up with the crosshairs and the crosshairs line up with the optical axis. Therefore, as we move the microscope back and forth, we should observe no change in the position of the beam or the crosshairs. One method that we found that was pretty effective was to adjust the position of the crosshairs using the tip tilt and then compensating for the beam displacement using the X/Y translation stage. We would then test the alignment by moving the microscope back and forth and checking to see if everything stays in the same position. If not, then we move it back closer to the laser and repeat. After aligning the microscope, we attempted to align a lens between the laser and the microscope. When the lens is properly aligned, we should see that the spot will stay in the same place as we move the lens back and forth.